Hi everybody, I am Joseph Giovanelli and I'm here today to present the paper Effective Data Preprocessing for AutoML, which I wrote with Yassine Bilali and Alberto Behi. So let's start. In a data analytics process, you have a data set, and after you have selected all the instances you are interested into, you have to apply a data preprocessing step. That is a series of transformations that make your data suitable for the next phase, that is modeling, where you apply a machine learning algorithm and get your results. Then you can interpret and evaluate them. Though this isn't a straightforward process, but far from it, data scientists keep iterating it over and over until they don't get results that are good enough. For example, they change the order of the transformations in the data preprocessing step or the machine learning algorithm in the modeling phase. So in literature, we distinguish two different problems. Regarding the data preprocessing step, we have the DPSO problem that aims to find the best order of the transformations according to the results, and then afterwards to tune each of the transformations because they have different operators and parameters. Similarly, for the modeling phase, we have the cache problem that aims to find the best algorithm and then tune its hyperparameters. So AutoML is a kit of tools that helps us to automate this whole process. And the main highlight is that it uses state-of-the-art optimization techniques like SMBO, sequential model-based optimization, that given a budget in terms of either time or configurations to visit, it provides suboptimal solutions in these huge search spaces. But the main drawback is that AutoML overlooks pre-processing. Indeed, this is the most complex step in this whole process. So let's understand why. In one of our experiments, we selected a list of transformations and a framework, therefore a scikit-learn, that gave us implementations of these transformations, but also rules, constraints that we can see on the right. Here you have a table where you have transformations in the rows and transformations in the columns, and each cell tells us if there is a precedence rule between a pair of transformations. So you can see this table as a graph where the transformations are the nodes and the cells are the edges. So we concatenated all the transformations together in all the possible ways according to the framework-related rules, and we generated this table on the right. Each of the combinations is a data pipeline prototype. We have 24 data pipeline prototypes, and they consist of an exhaustive set of data pipeline prototypes. So we optimize with SMBO, the data preprocessing step, with a time budget of 200 seconds, and the modeling phase with a time budget of 200 seconds. We selected a list of algorithms, therefore naive Bayes, KNN, and random forest, and also a suite of datasets, therefore the OpenML CC18 suite, that is an OpenML benchmarking suite. Then for each dataset and for each algorithm, we optimized each of the 24 prototypes of the exhaustive set because we wanted to find the prototype that achieved the best performance. So here in this chart, you can see that in the x-axis, you have all the 24 prototypes, and for each of them, the percentage of cases for which it achieved the best performance. You can clearly see two things. Firstly, there is no universal pipeline prototype, therefore a prototype that, if optimized, can achieve always or almost always the best performance. And secondly, there are too many prototypes to optimize if you want to select the best one. Indeed, for 60 datasets, 3 algorithms, 24 prototypes, and 400 seconds per run, these experiments took more or less 20 days. So let's understand how we tackle this problem. We figured that if we were able to select the most effective pipeline prototypes among the exhaustive set, Then we could be able to optimize all of them and afterward to select the best one. So firstly, we selected, as I said, a list of transformations and a framework to generate framework-related rules. Then we generated also heuristic rules. Those rules tell us for each pair of transformations, which is the order based on the literature that makes more sense. Then we also generated learned rules by running some experiments. Those rules tell us if a combination of two transformations can improve the performances or not. So here you have the three set of rules that we generated. Specifically, for the learned rules, we ran experiments just for the transformations pairs that we didn't know nothing about from the other two set of rules. The experiment setup of the learned rules was the same as the one we saw before. We optimized the data preprocessing step for 200 seconds and the modeling phase for 200 seconds with SMBO. But this time, for each dataset and for each algorithm, we optimize different prototypes, taking for example the transformation pair, feature engineering, and normalization. Therefore, the top left corner in this chart, we optimize two different prototypes, feature engineering first and normalization afterwards, but also normalization first and feature engineering afterwards. So here SMBO can choose to discard one of the transformations and leave just the other, or keep both and find operators and parameters for both. So we compare the results for each dataset and for each algorithm, the results of these two prototypes optimized, and we reported all the results in these charts. And here you can see clearly that the prototype normalization first and feature engineering afterwards is way more chosen than the other way around. So we ran also a statistical chi-square test to see the significance, and we concluded that normalization has to be first to improve the performance. We discarded all the other results since there were just one of the transformations or none of them, so they can be generated from both of the prototypes. Once we had all the rules, we took the union of the rules, or if you want to see these rules as precedence graphs, we took the union of the edges. And thus, we generated our set of data pipeline prototypes according to the rules as we did before. This time, we call this set effective set. And finally, we optimize all the 5 effective pipeline prototypes in order to select the best one, and then afterwards optimize the algorithm. So let's see how it performs. We compared our approach with the one that optimizes all the pipeline prototypes in the exhaustive set. The first thing that is worth to notice is that given a data set and a machine learning algorithm, our approach had run this procedure optimization just once. This was possible because we selected the most effective prototypes among the exhaustive set. Indeed, we were able to optimize all of them in the 200 seconds time budget assigned to the data preprocessing step. This thing was not possible to the exhaustive prototype optimization because in the exhaustive set, there were too many pipeline prototypes. Indeed, we repeated this optimization procedure for each of the pipeline prototypes. And we assume that the exhaustive approach could achieve better performance. Indeed, we calculated the normalized distance as the ratio between the performance achieved by our approach and the performance achieved by the exhaustive approach. but taking into account also the performance of the baseline. Therefore, where no optimization was applied. We plot the results with these three box plots, one per algorithm, and we observed that we were able to achieve results that were as good as 90% median compared to the exhaustive approach, but in much less time. We also compare our approach with the plain hyperparameter optimization because we wanted to see if assign a portion of the budget to the pre-processing could boost the performance. Indeed, we calculated two impacts, the pre-processing impact and the hyperparameter impact. These two impacts were calculated with the same formula that we calculated the normalized distance. Indeed, the pre-processing impact is the ratio between the performance achieved by our approach and the maximum between the performance achieved by our approach and hyperparameter approach, taking into account the accuracy of the baseline as well. We normalize these two impacts and then we plot the results. In these three bar charts, you can see in the x-axis the data sets, and the orange bar is the impact of the pre-processing, meanwhile the blue bar is the impact of the hyperparameter optimization. We concluded that assigning a portion of the budget to the pre-processing can boost the performance, according to our experiments, in 73% of the cases. So all in all, we conclude that there is no universal pre-processing pipeline prototype, therefore a prototype that, if optimized, can achieve always or almost always best performance. We also conclude that pre-processing can boost the final results, and we also see that our approach achieved results that were as good as 90% median compared to the exhaustive approach, but with a cost that is 24 times smaller. In our future works, we would like to study the datasets that do not react well or do not react at all to data preprocessing, but also to extend our approach with a meta-learning module. Therefore, that giving a dataset and a machine learning algorithm can recommend the most effective prototype, and hopefully we can get some insight. So thanks for attention.